Okay, so in this example we have a homogeneous rectangular plate that's released from rest with its upper surface being horizontal, and we're asked to assume that the pin at O to be smooth. And given this information, we're asked to determine the maximum angular velocity of the plate as it rotates about its pin support. Now to determine the maximum angular velocity after a change in position, we know we're going to want to use the work energy method. But before I do that, I want to note what configuration this plate would be in to have maximum angular velocity. For us to have maximum angular velocity, we would need the potential energy of the plate to be converted to the extent as much as possible into kinetic energy. And so I would like you to note at this juncture that when that happens, the center of mass of the plate is going to be immediately below point O. So if I go ahead in this problem and choose my potential datum to be here, we can note that initially we're located a distance of d over 2 down from the datum. And that the final step will essentially be on the diagonal of a triangle, where we have here this height is still going to be d over 2, but this right here is going to be the 1.5d, so 3/2 d divided by additional 2. So I can call this, if I call this h1, I can call this distance to be h2, and note that h2 is the hypotenuse of a triangle. And so if I square that hypotenuse, this has to equal, in this case, 3d divided by 4 quantity squared plus d over 2 quantity squared. Okay, I'll use that in a minute. That's just a little geometry. I also need to draw a free body diagram for this system. So if I do that, I know in terms of forces, I'm going to have the weight of this thing, mg, and I'll have some reactions here at point O, which I can call OX and OY. The important thing from this free body diagram is there's no forces here which contribute non-conservative work, and so I can write down in this case a relatively simple work energy expression. So here I'll have T1 plus V1, the sum of the initial kinetic plus potential energies, plus the non-conservative work done moving from state 1 to state 2, has to equal T2 plus V2. In this case, I know the system's released from rest, so T1 is going to go to 0. I've also noted that no forces contribute non-conservative work, so the third term will go to 0 as well. I can now find the remaining terms. So V1, the center of mass is initially a distance d over 2 below, so I'm going to have this is minus m times g times h1, which is d over 2. The potential energy at the second state is going to, in this case, if we want to treat it in the state of pure rotation, we can write this as 1/2 times I about O of the system times omega 2 squared. And since we want to find the maximum angular velocity, this seems to be a good approach. So if I want to re-expand this, I can write this as 1/2 times I about g plus the mass of the plate times the distance between O and g, which in this case, in this state, is simply going to be h2 quantity squared. I'm going to multiply that by omega 2 squared, and then I can note that I about g for a thin plate is simply given by 1/2 times 1/12 m times, in this case, the width, which is 1.5 d quantity squared plus d quantity squared. I'll add to that the term from parallel axis theorem, so I'll have an additional m times h2 squared, and that'll be times omega 2 squared. The potential energy of the second state, what we'll call V2, is just going to be given by minus m times g times h2. If you take these three expressions and plug them in with the two zeros we've already determined into the work energy equation, you can get back the angular speed of the system, namely omega 2, and then we can note that this thing's rotating counterclockwise, so we're simply going to get back an angular velocity of omega 2 in the k direction. Okay, from here on out, this is a relatively straightforward substitution exercise, and one I know you got well under control. So I'll go ahead and leave that up to you to do, and simply wish you the best of luck. Take care, everyone.